Section 7.8, Applications of Matrices and Determinants. Area of a triangle with vertices at x1, y1, x2, y2, x3, y3 can be found using this formula. Each row of the determinant used here is the x-coordinate and y-coordinate. Third column will always be a column of ones. Each ordered pair gets put in row 1, column 1, x and then y, x2, y2, x3, y3. Column 3 will always be ones. The plus or minus 1/2 out in front, you will not get two different answers. You will either use positive 1/2 or negative 1/2, depending on which one would yield a positive area. In other words, if you evaluate the determinant and it's negative, then you're going to multiply it by negative 1/2 so that your area is positive. If you evaluate the determinant and it is positive, then you're going to multiply by positive 1/2 so that your area is positive. So looking at our first example here, find the area of a triangle whose vertices are 1, 0, 2, 2, and 4, 3. This formula tells us that we can take plus or minus 1/2 times the 3 by 3 determinant, where we use the ordered pairs 1, 0, 2, 2, 4, 3. Third column is always a column of ones. From here, you can go to your calculator and put this determinant into the calculator. Go into your matrix menu, edit. We want to put in a 3 by 3 matrix here and put in the values 1, 0, 1, 2, 2, 1, 4, 3, 1. Once you have those entered in, exit out of that menu, go back into your matrix menu, over to math. We want to evaluate the determinant. Back into your matrix menu once again, the determinant of matrix A, hit enter, and there is the value of the determinant. So now going back here, we now know that the value of this determinant is negative 3. So that means we want to use negative 1/2 so that we get a positive area. And the area of this triangle would be 3/2 square units. Next application of determinants is the test for collinear points. 3 points x1, y1, x2, y2, x3, y3 are collinear, meaning they lie on the same line if and only if that exact same determinant that we just dealt with is equal to 0. And that should make sense to you, because if we have any 3 points in the coordinate plane that are not collinear, in other words, that we cannot draw a straight line connecting all 3 points, then those 3 points would make up vertices of a triangle. So the only way that it would not make up vertices of a triangle is if all 3 points were on the same line, meaning then that this determinant would have to be equal to 0, because there would be no triangle, therefore no area. So determine whether these 3 points are collinear. We're going to set up the exact same determinant we just did for the area, negative 2, 1, 1, 7, 5. Third column, remember, is always ones. Once again, I'm going to go to the calculator, and I'm going to plug in this determinant. So I'm going to go into my matrix menu again, over to edit. We still want a 3 by 3. This time the values are negative 2, negative 2, 1, 1, 1, 1, and 7, 5, 1. Exit out of that menu. Back into your matrix menu. Edit. Matrix A. Sorry, not edit. We want to go math. Determinant of matrix A. Hit enter. There's the value of the determinant. So this determinant we know is equal to negative 6. Since it is equal to negative 6, that means that these 3 points are not collinear. There is a triangle formed, therefore the points cannot lie on a straight line. Make sure when you are done with these types of problems, you are not just saying what the determinant is equal to, but you are given the value of the determinant and then interpret your answer by saying it is collinear or not collinear. The only way that they are collinear is if that determinant is equal to 0. Third application of determinants we're going to talk about is Cramer's rule. Cramer's rule gives us another way of solving a system of equations. We know substitution, we know elimination, we know reduced row echelon form. Cramer's rule is a fourth way in which we can solve a system. It's going to look very complicated here, but it actually is very, very simple. Notice in our formulas here, our x1, x2, xn are whatever different variables we might be solving for. Let's say xyz, xyzw, a, b, c, it doesn't matter the variables. And notice that for each one, this bottom determinant is always the same. So once we evaluate it for one of the variables, we're going to know that value. We don't need to go and do it over again. Solve this system by using Cramer's rule. Nice thing about Cramer's rule is we can solve for whatever variable we want right away. Where sometimes substitution or elimination, we may be wanting to solve for x, but it's easiest to eliminate x's first, and then we have to find y, resubstitute in, and find x. Cramer's rule, we can solve for a variable directly. In Cramer's rule, for solving here first for x, first of all, we need the equations in standard form here. X, y, constant on the other side. They already are in that form. Our denominator determinant is always a determinant of the coefficients on the variables. So in this case, 4, -2, 3, and -5. Our numerator determinant will be almost exactly the same. The only difference is whatever variable it is you are solving for, in this case we want to solve for x, you are going to take that column out. So I'm going to take the 4 and the 3 out because that's what we're solving for is x, and I'm going to insert the constants in that column instead. The rest stays the same. Evaluate now the 2 by 2 determinant. Up top, we get -50 minus a -22 is -28. In the bottom, -20 minus a -6 is -14. Divide that out, and we know x is 2. So there's x. Do the same thing to find y. Remember, we now know what that denominator determinant is, and that's the same no matter what variable we are solving for. So we know this bottom is going to be -14. Our top determinant now is going to change because now we are solving for y. So we take our same denominator determinant, but now I'm going to take out the y column and put in the constants. Evaluate that. 44 minus 30 is 14 over -14, and y is -1. So the solution to this system is the ordered pair 2, -1.